Gonna get moving here with the third section of material, and I've communicated with some of you guys already about what this third test is going to be on. I don't know. I'm still figuring this out as I go. The general plan is I'm going to do a little bit of this geology stuff. I'm going to do a little bit of geomorphology. We'll get into the differences between those two terms, but it's going to be rocks and some other stuff that we cover. And honestly, I know that some of you guys you want to get moving ahead just to deal with this thing or that thing, or just deal with the craziness of reality right now. I get it, but also I'm scrambling to try to get this stuff together. I've got multiple classes I'm working on, so this is going to be I'm just going to be chipping away, doing this as quickly as I can. But the good news is, I'm not. The test isn't going to be nearly as extreme as it would have been had the semester been normal. So I'll let you guys know, get a study guide together. I'll let you know with plenty of time before that test is going to occur, like exactly what we're going to focus on. But just keep reading through the book, because I'm still expecting you to do those homework questions. So, and that will help you study for the test. Even if some of these things we don't cover, the ones we do, you'll be set, right? So just start with chapter 8, which, is even stuff I'm not going to be talking about, but still read through it, answer these questions, and let me know, however you want to. Email me if you want to request some kind of office hours meeting or whatever, we can do that. Just let me know if you're stuck with anything on these textbook chapters that I'm not going to be discussing, right? And I'm not going to be discussing them just in the interest of time and not giving you guys too much work. So you can deal with all of this stuff that's going on in your lives right now. All right, so that said, let's get moving on to this batch of geologic stuff. So today I'm going to get into physical geology, which is going to be pretty straightforward. We'll get into, just what rocks are, as well as minerals, and we'll be classifying this stuff, talking about igneous rocks versus sedimentary rocks and all that stuff that you've probably gone over in elementary school to a certain extent. We'll cover it at the college level here, but that's the plan for today. And then the next one I'll be putting together is the historical geology, which is less about what type of rock is this and, this classification stuff, and it'll be more about, thinking like a geologist, which is quite useful in geography. And we'll get into just this ancient planet, how it came to be, how we know it's ancient, that kind of stuff. All right, so that is the plan. So with geology, we're dealing with the study of really the material component of the Earth, which is a fancy way of saying the rocks and stuff. All right, what is the Earth made out of? Now, it's not all rocks, as we'll see a little bit, but that's just kind of generally how we can think about this. It's what is the Earth made out of, and it turns out there's a lot of different stuff in the Earth. We'll cover some of that today, but not just what is it made out of, but how did it come to be. All right, and with geology, it's actually, it's, my God, I would never be a geologist. Bless their hearts, it's too nerdy. For me, all this chemistry and stuff like that. But it is a quite fascinating discipline when you look at it, just because it really came into being at this kind of Enlightenment era of scientific discovery in the 18th and 19th century. So a lot of early important work was done back then. We'll cover some of that next time. But then we have stuff like the theory of plate tectonics, which I'll discuss, I think, 2 lectures from now. I'll be covering exactly what that is. But that's a pretty remarkable story, because that came into being really at the end of the 20th century was when it was finally accepted, when we started changing textbooks. It radically changed the way we understand that the Earth functions. So there's, some classic old thought, but there's also all sorts of new stuff happening today. So it's a pretty dynamic and evolving discipline, and pretty cool to cover, right? So that's what we're going to be looking at. And I will be talking about plate tectonics I'll spend, a good hour and a half chatting about the theory of plate tectonics. What is it? What does it mean? How did we figure this stuff out? So I'll cover it in detail, but just to kind of let you know what we're talking about right off the bat. With plate tectonics, it's effectively saying that the outside of the Earth, so the Earth's crust, its outer shell of rock, is in fact broken. Okay? So it's broken into individual plates. And so we can see that in here, like we have the Pacific plate right here. We have the North American plate right here. And we actually, being in the Antelope Valley, being in northern Los Angeles County, we're right at this border between the North American plate and the Pacific plate. Try to think, what could that border be? It's got a name. You've all heard about it. I'll wait. That's right. Of course. Thank you for shouting it out. Yeah, of course, it's the San Andreas Fault, right? So the San Andreas Fault is that boundary between the North American plate and the Pacific plate, where these two sections of the Earth's crust actually meet. And if you want to know exactly where it is, I don't know if I've talked about this with you guys at all yet, but if you're curious to see it, because we all kind of know it's here in the AV, but we don't necessarily know exactly where. If you get on the 14, heading south, down toward Acton, you'll be driving along and you'll be approaching Avenue S, that exit, as you kind of go up a little bit and then down, and there's that Avenue S exit. As you're going down, you're entering the San Andreas Fault itself, right? So that little valley there that runs along that area, that's the San Andreas Fault. And as you keep driving, and then you go up the hill, and then drive back down again toward Acton, you're exiting the San Andreas Fault and getting away from it, and you're now on that Pacific plate. Okay, so we live in a pretty cool spot where we've got this boundary, we can actually see it, and we'll talk more about that maybe at some point. I don't know if I'm going to be talking about earthquakes, just again, in the interest of time, but you've got readings on that stuff. But that's the idea with plate tectonics, is that this outer layer is all broken, and not only is it broken, and therefore these different plates are independent of one another. So these little independent, or I shouldn't even say little, these massive independent sections, like, most of the Pacific Ocean, North America and all this other stuff up here in the Arctic. So we've got these massive areas, but they're freely floating. That's another key thing. And if we look over here, we've got the inner core, the outer core of the Earth. I'm skipping all of the interior of the Earth stuff. But we got that stuff right here. Where'd my cursor go? There we go. This stuff in the middle. We've got the mantle. And up here toward the end of the mantle, we have what's called the asthenosphere, which is this kind of just weird anomaly that exists. It's plastic, meaning that it behaves kind of like Play-Doh or silly putty or whatever. It's not quite liquid, not quite rigid. It's this kind of gooey, silly putty-like thing, and that actually it helps us float up here on the plates themselves. And you don't notice it. It doesn't feel like we're floating or that we're even, moving, but we are. Our plates are constantly moving. They're independently floating on this stuff, and that's what plate tectonics is all about. It's not just that it is the existence of these plates, but how these things move and interact and crash into each other, or pull apart from each other, or whatever. Okay, and I'll get into it. I'll spend plenty of time talking about how that exactly works. But that's the general idea, okay? And that's pretty important stuff. So it'll be important that you guys actually understand exactly what's going on. But we'll get to that later. So with geology, we typically break it into two sub-components or two sub-disciplines. We have physical geology, and then we have historical geology. And so today, as I've said, we're going to cover the physical side of geology, where we're simply looking at the stuff the Earth is made out of, right? The atoms, the minerals, the rocks, that kind of stuff. We have the, oil derrick here, energy in terms of like petroleum, fossil fuels, stuff like that has been a big component of physical geology. And we'll talk about, the rock form of these hydrocarbons and fossil fuels and all that stuff, but oil fits into there as well. We wouldn't classify it as a rock, but it's definitely this material in which, at least part of the earth is made, right? So it's, to be a physical geologist, what, a number of these folks who study physical geology would do be to look at the earth, figure out exactly where to find oil or other important resources that could then be extracted or mined in some way and then used for industrial purposes or whatever. Right? So the physical geologists have kind of this practical approach, right, to this stuff. Where they're looking for resources, maybe from an engineering standpoint, knowing where you can build, what kind of material you can build onto, or stuff like that. That's what a physical geologist would focus on. Whereas historical geology is more looking at telling a story about the Earth and getting a sense of how the Earth came to be and how it's changed over the years. So the Earth is how old? That's right, 4.6 billion years, right? So that's a number that's important to commit to memory. And I don't think I've made you guys commit that to memory yet. But it's something now it's good to know that, right? That it is 4.6 billion years old. And when we talk about historical geology, that'll be important. I'll get into why it is important to know how old the Earth is, as well as how we know this, right? How do we know that the Earth is that old? So we'll get into that stuff. But it's not so much looking for important resources or whatever, but just trying to get an idea of how has the Earth formed, changed, all of that kind of stuff. All right, so we'll cover that next time. In the meantime, we'll just focus more on the stuff of which the Earth is made. And I'm going to be kind of abstract with a lot of this, talk about just kind of general classifications and types of rocks. But it is good to know, too, my fellow Californians, that this is a fascinating place to study geology, as well as we'll see, geomorphology when I get into that and what that actually means. But it's because California is, really, it's because it's new, right? Geologically speaking, California is a brand new location. North America, it's been around, forever. At least hundreds of millions, if not billions of years in some places. We've got rocks in Canada that are 3.9 billion years old. So we've got these really ancient components to North America. But here on the edge, here in California, we're brand new, right? We're millions of years old, whereas a lot of other stuff is billions of years old. And it also, that's cool, just that we're new, but it's also when you look at how the California came to be built, it's bizarre. Like we've got the granite of the Sierra Nevada, which is more or less, that's kind of easy to figure out how that works. We'll talk about that in a little bit. But we've got other stuff, like along the coastal range, or just the coast of California and running up through, Oregon and the Pacific Northwest and all that. It gets crazy, where we've just got other rocks pushed up against North America, shoved up here. It's like this weird patchwork of just craziness. Right? If you want to be a geologist and have a relatively easy job, go to the East Coast, where it all makes sense and it's all the same stuff, or it's stuff that you would expect to find where you find it. Over here, it's bizarre. It's crazy what's just kind of thrown about. So it makes it for more of a challenging job to try to understand the geology of this state, but it also helps to explain just like why this place is so attractive, why we want to live here, why people want to live in California. It's because it's gorgeous, and a big part of that is because of the crazy geology, which leads to the fantastic weather and some of that stuff that we've already talked about. Right, so California is a great place to be looking for this stuff, and even for you guys being here in the Mojave Desert, that's even better because you don't have all these obnoxious, trees and plants and nonsense to get in the way of the rocks, right? Out in the desert, you can see all this stuff with minimal effort. And I think we'll see some examples of that today. All right, so we have the crust of the Earth, and just I'm skipping through the different, interior components of the Earth itself, but we go core, then mantle. So core is on the center. That's the inside of the Earth. Then we have the mantle around the core, and then this very thin but very important outer shell made up of for the most part, kind of rigid rock, right? The stuff we're walking on when we're, walking anywhere on the surface or even at the bottom of the ocean. That's the Earth's crust. Okay, and we'll talk more about these layers when we get into plate tectonics. I'll cover some of this stuff when it becomes useful to kind of help explain how these plates are interacting and that kind of stuff. But within the crust, we have these 8 primary elements with which we're dealing. And if you look at this pie chart, you can see most of it's oxygen and it's silicon. That makes up the majority of what we've got in terms of elements, these most basic, units of just stuff, of matter out in the universe. We've got primarily oxygen, primarily silicon, but you can see some other stuff in here. Okay, with this, what's kind of cool about this is even though we're pretty much working about 8 of these primary things, we can still have this incredible variety of the material that's actually, making up the crust itself. So when we have these elements bond together, okay, little atoms of elements, when they bond together in a specific way, we get minerals. Okay, so atoms, tiny microscopic stuff we can't see, right? Little teeny tiny invisible things. But if we have some little teeny tiny atoms of oxygen and some of silicon, and they get attracted to one another, bond together, and bond together in a specific way, so they have this crystalline structure, they will produce minerals. Okay, like this example up here at the top, this is amethyst, which is silicon and oxygen atoms bonded together in a specific way. It's effectively, it's purple quartz, right? It's the same stuff. Quartz has silicon and oxygen in it as well. But because, and again, it all has to do with how these things are bonding, we not only get these crystals here, and this is all natural. This is the atoms doing their stuff. It's not, people going in, jewelers cutting this stuff up. It's the way in which these atoms are bonding. It's that crystalline structure, right? And this specifically, too, we get that purple coloring in here, all because of how these things came to be. Okay? And what we'll see is that you can get multiple minerals stuck together, and we'll get into how exactly they get stuck together in a bit. But minerals will then go on to make rocks. Okay? So just going from smallest to largest, typically we have atoms, right? Which are the little units of these elements. And then when these atoms bond together, they produce minerals, right? And they get to the point where we can actually see this stuff. It's no longer this microscopic stuff. They've bonded together, okay? And so they bond together, and then with more processes that we'll get into, these minerals can go on then to make rocks, right? Hopefully that makes sense. Here's another example. Quartz, like I said, it's also silicon, oxygen, bonded together, distinct crystalline structure. It has this white to clear coloration, so different from the amethyst. But the difference there, what makes, because the chemicals, the elements in both quartz and amethyst are the same, but it has to do with how these things are actually bonding together, right? The actual, inner workings of the thing will make the mineral itself. And quartz we find everywhere on the continents because it's incredibly resilient, meaning it's just tough. It's a tough mineral that, it can get beat up and broken down, and we'll cover weathering and erosion when we get into geomorphology. But quartz, even though it can be, yes, broken down, it's still tough enough to where it doesn't dissolve. It's not vanishing. Dissolving, completely or breaking apart completely or whatever. We just get, smaller bits of quartz. That's what a white sandy beach is. It's the quartz inside there as well as some other felsic materials that are making that up. All right, so that's quartz. It's an example of a mineral, and it's one we see everywhere because it's a pretty tough mineral. And this kind of goes back to the idea of, quartz and amethyst being the same on the inside, but totally, not even totally different, but just different. But this is an example of same on the inside, but radically different. Both diamonds and graphite they're just carbon. All right, they're atoms of carbon that have bonded together, but even though they're the same on the inside, they're radically different, right? Diamonds, expensive, very valuable, pretty shiny things that we humans love for whatever reason, because we like pretty shiny things. And they're also valuable from like an industrial standpoint, making, saws and stuff like that, because they are so tough, right? It's the hardest substance on the earth. So yeah, having the diamond, saw blades and stuff like that make it so you can easily cut through stuff. So that's carbon. But then graphite is that, pencil lead, right? It's the stuff we have inside our pencils. It's incredibly soft, which is why it works for pencils, because it leaves that streak on the page or whatever, right? That's the graphite is just falling apart because it's so delicate and wimpy, right? Still carbon, but radically different. And it all has to do with how these carbon atoms actually bond together, all right? The geometry of how these little atoms stick together, that will all determine whether it's this incredibly tough, incredibly valuable material, or this very soft, still useful, but not quite as fancy material, right? So the actual bonding itself, something we're not really going to worry about in here because we want to get to the big stuff. That's very important for determining what a mineral is going to, actually be, right? Or what mineral will come from these different atoms. All right, so there's that. Now, a rock we can define as being an assemblage of minerals, right? Meaning a rock is assembled from these different minerals. Okay? Granite is an example of a rock that we'll talk about quite a bit, simply because it's everywhere, and it will be important to understand some of the other stuff that we talk about, like with plate tectonics or even geomorphology and some of that. But granite forms when we have these four-ish minerals. We can have slightly different variations of this stuff, but it forms when we have quartz, which is a mineral, this mica down there in the right corner, lower right corner. That's another mineral, hornblende in the lower left, another mineral, feldspar, another mineral, and so they get stuck together. They lithify. We'll get into exactly how this works, but lithify or lithification refers to the actual creation of a rock, right? When something turns into a rock. And remember, I think I mentioned this like in the first week of class. Lith, right? Lith, refers to rock or geology of some kind. Okay, so when we see something that has lith in it, like lithify, we're talking about rocks in some way. All right, so granite is this assemblage of these four different minerals that get stuck together, and we can see that. And why I use granite as the example, it's got this large grain size, so it's very easy to see Where you see white in the rock, that's the quartz. And where you see that kind of tannish, pinkish color, that's the feldspar. And then the darker stuff could be the mica or the hornblende or whatever, right? So we can see these different minerals in there. We get a sense that it's made up of different things, right? And that's completely what a rock is. Right? We have some exceptions. We're not going to worry about it, like obsidian, which is super cool. And it's a shame too. I mean, if we were in the classroom setting, I'd have my box of rocks like a complete nerd and be passing this stuff out, so you guys could actually feel it, see what it looks like up close and all that. But obsidian is just fantastic. We've got the two pictures there. It's both obsidian. One's this big mountain of the stuff that's kind of up near Mammoth. But then there's a better, just shiny volcanic glass sample in that rightmost image there. But yeah, obsidian is this volcanic glass that's just gorgeous to look at. You can work with it easily to produce sharp edges, which is why a lot of indigenous people throughout the Americas would use this for knives and projectile points, arrowheads, that kind of stuff. Use that, for these stone tools, and we'll get into exactly how that forms. But technically, it's not made up of minerals because the minerals never really have time to crystallize. All right, I'll get into that later. We'll also see some examples of organic material making up a specific type of rock. The minerals of which we're talking about here, from a geologic sense, are inorganic, right? Meaning that they aren't made up of once living things. Right? It's oxygen, it's silicon, it's that kind of stuff it wasn't alive and then died and made this stuff. It's non-living stuff coming together to make minerals to then make rocks, right? So we have some exceptions. Don't stress over it. We're not going to get too nerdy about this stuff. Just know a rock, it's an assemblage of minerals. All right? All right. But of course, it's not that simple because we have rocks, but we have to classify these things because that's what scientists do. They love to put stuff into these little categories. That's how they roll. And so we do that. So any rock we find is going to be placed into, or can be placed into, one of these three categories. All right, so we have igneous, the first one I talk about, sedimentary, get that next, and then I'll close with metamorphic rocks. Okay, so again, any rock we see can be fit into one of these three categories. Okay, and so that means, as we're going through, I'll be giving you, the criteria, how we classify this stuff, and you just want to be aware of, how this actually works. So if I present you with some stuff, or maybe, let's just say maybe at the end of this lecture, I quiz you on some of this, you can go through your notes, you can think about this stuff, and you can easily say, aha, yeah, this thing here, it's got to be igneous. This one, got to be metamorphic. And I know it's metamorphic because of this and this and this, right? Something along those lines. So that's the goal for today. And this is mainly what we're going to be talking about here. What I want you guys to really take from this is what makes these things different. Okay? And another thing that's important to realize is how this rock cycle works. And with the rock cycle, there are very few good diagrams of this stuff or drawings or whatever of the rock cycle. They always look something like this, which is just terrifying for most, undergraduate students, first year students especially, who are reading through a textbook or whatever, and they see something like this, and you go, oh, no, too much, right? You get more than like 3 or 4 boxes, and you have more than 3 or 4 arrows. It's so easy to just move on, right? Assume, it's probably not that important, and move forward. All the rock cycle is saying is that any rock at any point, let's just say today, if I find an igneous rock, okay, that rock down the road, and it could very well be hundreds of thousands, if not millions, if not billions of years down the road. But that rock could turn into a different type of rock. All right, so if it's igneous today, later on it could become a sedimentary rock. And then later on, that sedimentary rock could become a metamorphic rock. And then that metamorphic rock, it could melt down and cool and become an igneous rock again. And so on. Right? So it's simply saying rocks that exist today, they're not always going to be like they are. Right? They can turn into this other type of rock. Okay? Another way to look at it is just to say that the Earth is not ever done. We tend to think of the continents themselves, the rocks on which we're walking and all that. It's just kind of, I don't know, the background. It's something that is just there and it's not changing. It's just always there, right? Like we people might change, but nature is just going to be nature, right? That's wrong. That's completely wrong. The Earth has changed quite a bit. It's constantly recycling and transforming and doing all this stuff. I'll introduce how that actually works here, today. But with plate tectonics, what this has, kind of helped us understand is that, yeah, it is transforming. And that's also why it's kind of hard to get some of this evidence for what happened in the past, because rocks that were here at the very beginning, 4.6 billion years ago, they're not around anymore because they've changed, right? Maybe there were igneous rocks that cooled, 4.5 billion years ago, but they've since been eroded and they turned into sedimentary rocks. And then those sedimentary rocks got shoved deeper in the earth through other, processes, and that turned into metamorphic rock and so on, right? So the stuff that was here at the beginning of the Earth's formation isn't necessarily here today, right? And I can't remember because stuff is getting out of order and I don't even know. I mean, you guys are there too, right? You have no idea what day it is, what's happening, because you're hopefully just staying inside like good people, good citizens of the world. And I'm going to try to, just kind of talk a little bit about this whole idea, just if anybody's not sure of why like we should be staying inside or why we shouldn't be treating this like just super spring break or summer vacation or whatever. I'm going to try to produce something in a little bit just so you guys can all, make sure you're aware of what's happening here. But anyway, yeah, I don't even know what I'm talking about. That's how crazy everything is going on here with all this stuff. But the point is, yeah, I totally lost my train of thought where I was going with that. Look, the point is, rock cycle just means rocks are churning about, changing. Oh, that's okay. Now I got it. See, now I'm back. Now I'm back. I'm not doing well. Clearly, I wish you guys could see me right now. I have a beard that's like 3 feet long. I'm just in a robe and slippers right now. It's just it's chaos. Now, what I was saying is I don't know if I was talking about, which I think I might have normally talked about with another lecture that I'm not doing for you guys. But the rocks that we have around the planet that tell us how old the Earth is, we don't have that many. We've got some cool zircon crystals in Australia. I just mentioned that we have these rocks in Canada and the Canadian Shield that are 3.9 billion years old. We've got these 4.3 billion year old crystals in Australia. That's what we've got. We've got these little individual spots around the globe that tell us that what's going on. That 4.6 billion year number that I've given you for the age of the Earth, we get that through the dating of some specific rocks and minerals and stuff around the Earth. But it's not as easy as just, looking around picking up any rock, because so many of those original rocks are long gone, right? Because they've been destroyed, transformed, something along those lines. And when we get into plate tectonics, we'll see the exact processes for how this stuff can happen. Okay? Hopefully that makes sense. All right, let's move on. I don't know. Okay, let's move on. All right, so we're going to start with igneous. And with all of these categories, we have these subcategories or subclassifications. So like we have igneous rocks, but then we have two specific types of igneous rocks, right? So igneous simply means, in fact, the word itself means fire formed. Okay, I think this one's Latin. I can't remember. But it means it's formed from fire. It's when we have incredibly hot, liquid, therefore melted or molten rock, right? So this incredibly hot stuff, it's so hot that it's actual liquid stuff that's flowing. When that incredibly hot rock cools and solidifies, or what we call lithifies, it's an igneous rock. Okay, so any rock that came from this incredibly hot liquid stuff, and once it cools, that rock is going to be called an igneous rock. Okay, now with this incredibly hot liquid stuff, we have two different types of molten rock. Okay, we have magma and we have lava. And honestly, there's no real difference necessarily, chemically speaking between these things. It all has to do with where we find the stuff, where we find this molten rock. Okay? So magma is any molten rock that's underneath the surface of the earth. Right? So if it's underground and it's incredibly hot and it's liquid rock, it's magma. Okay? As soon as that magma works its way up enough to break through the surface and come out onto the surface so we can see it, like this image here would show, we call that lava. Okay? So magma and lava, same idea in that it's molten rock, but magma is simply that molten rock that's underground. Lava is molten rock that's above ground. Okay? Hopefully that makes sense. And so, with our igneous rocks, our two different types. Our first subtype here is what we call an intrusive igneous rock, which is when we have magma cool and then become a rock. Okay? So intrusive igneous rocks form from cooling magma, meaning that these rocks form underground, right? They don't actually make it up to the surface. What happens is, we have convection. We have this idea that hot stuff rises. All right, so we have inside the earth, incredibly hot rock. It's molten. It's moving around, and it wants to move up because hot stuff rises, cool stuff sinks. All right, so this hot magma is working its way up toward the surface, and it gets stuck. It goes into cracks in other existing rocks, and it just, can't go any further. And so it's stuck there, and it just starts to cool off. All right, it's risen enough to where it gets away from some of these initial, sources of heat that made it molten in the first place. So it is starting to cool, but it's still pretty hot. And we'll get into the temperatures inside the earth and how that works. Again, we get to this tectonic stuff, but it's just deep inside the earth, it's very hot, all right, compared to up here on the surface. So even though it's not as hot as it once was, it's still really hot. So it cools quite slowly. Like it can take years for this stuff to actually fully lithify. All right, that's the idea here. So it's a very slow process, and what that means is that we have enough time for the different stuff in the magma to bond together, to crystallize. We can actually see minerals start to form. Right? So the minerals have time, and they develop what we call large grain sizes in the resulting rock, meaning that it's very obvious where these different minerals exist in the rock. Okay, so an intrusive igneous rock, one that comes from cooling magma, it's going to cool slowly, and therefore it will have large grain sizes. And we've got, pictures coming up here, and I'll show exactly what I'm talking about, but that's just how these things work. So I'll give better examples here in a moment. Okay? Some terms here, just kind of generic stuff that's good to know. An intrusive rock is also called a pluton. All right, from the Roman god Pluto, that's what we're dealing with here. So it's a pluton is simply the same thing as an intrusive igneous rock. Okay, so we can use it either way. And then a large pluton we call a batholith. It sounds kind of cool. And by large, we're not getting into exact criteria here, but like the Sierra Nevada, all right, which are all granite, which is an intrusive igneous rock. The Sierra Nevada mountains themselves, the ones here in California, they're the result of this massive batholith that's just, hundreds of miles long, underneath California, forming and then eventually working its way up here through tectonic activity and erosion and stuff like that. All right, so batholith, when we're talking about that, we're talking massive amounts of these plutonic rocks. Okay, so just, some terms that are kind of useful here to know. So that's intrusive. Now, the other type of igneous rock is an extrusive igneous rock. And these are rocks that are formed by cooling lava, right? So where we now have molten rock on the surface, it cools, and it cools quickly because it's much cooler up here on the surface compared to, miles beneath our feet down in the earth. And so this faster cooling produces fine-grained rocks or small, crystal sizes or grain sizes in the rocks themselves. All the elements in here that could, slowly form and join together and have these distinct crystalline shapes and blah, 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 they don't have time to do that. So they quickly form. So we have much smaller grain sizes, and these rocks just kind of look more consistent throughout. Again, I'll give some examples of that. Okay, and so these rocks we can also call volcanic rocks. And they come from volcanoes, which are things up on the surface where this magma can actually escape. All right, and so it's magma again when it's inside the earth, but as soon as it leaves a volcano, we call it lava, and then it cools quickly up on the surface, and we get these extrusive igneous rocks or volcanic rocks. All right, another way to think of it too: extrusive, exterior, it's on the outside. Intrusive igneous rocks are on the inside, right? So that kind of helps too as you're trying to memorize some of this stuff. And this, let's skip this. Hey, here, good. We've got some examples here. All right, so granite is an intrusive igneous rock. We already saw it before, but this is what I mean by the large grain size. We have the different blacks and whites and tans and stuff in here, right? We can see the different minerals that make up this rock. Okay, so that's what a large grain size means. So we know this thing cooled inside the earth. And when you look at it, the fact it doesn't look like it's actual different types of minerals that have been glued together. We'll see examples of that with sedimentary rocks in a little bit. But instead, this you can kind of envision how this stuff, was something that melted and then cooled. It almost looks like it, was poured and cooled in this area. Not that it was pieced together, glued together like a puzzle being placed together. Right? So it's an intrusive igneous rock. We can tell that because of the large grain sizes. And this term felsic right here means it's rich in feldspar, so there's the fel, and then silica, right? And what does it, we may or may, I don't know how much we'll dwell on the importance of these distinctions, but felsic means, yes, rich in feldspar, rich in silica. It typically also means it's lighter in color. Okay, so it's going to, while there's some dark things in here, if we look at granite, big areas like you go out into the Sierra and you look at all that granite, it's a light gray to white that most of this stuff looks like, right? So it's lighter in color. If we may get into more of this or not, but just know feldspar, rich in silica, lighter in color compared to the other type, mafic stuff that I'll talk about in a bit. Okay, rhyolite is another igneous rock, but this one is extrusive. Okay, so this means it's lava that cools. It produces rhyolite. It's fine-grained in that we can see, there's some different stuff here, a little, flecks of different colors in here, but it doesn't look like the granite itself, right? It's pretty consistent in there. They're tiny little things, not these big, obvious, different minerals in there. So that's what we mean by fine or small grain stuff. It's also felsic, okay? And we can see the light color. It's typically kind of a light pink lavender color that we find. And what's cool about this is that this is found in the same place where we find granite. Like here in California, we find rhyolite, and it's the idea that if this magma got stuck inside the earth and it cools, it's going to make granite. right? But if the same material works its way up to the surface, comes out of a volcano, cools quickly up here on the surface, it's going to produce rhyolite. And it's at this point you'd be holding a sample of granite and of rhyolite, and you'd see, even though they're the same thing internally, right? They've got the same ingredients, they just feel different. They're clearly different rocks. And so how these things actually cool, how they lithify, is incredibly important into what kind of rock is going to be, left over from the end of this process, right? So rhyolite, granite, same stuff internally, but because one's extrusive, one's intrusive, they're radically different rocks. So what's really neat is that obsidian, that volcanic glass, that is lava, magma as well as lava that would have been rhyolite if it cooled at a normal rate. But if it cools even faster, like it hits a pocket of water or whatever, and it just instantly cools, we get obsidian. All right, so meaning obsidian, this brittle, transparent to translucent, beautiful volcanic glass, it's the same stuff as granite, it just cooled in a much different way, right? So it's a different type of igneous rock. All right, so there's some examples there. What we find around here in California. Now, basalt is another extrusive igneous rock, but this one is mafic. Okay, and we can find basalt like technically on the surface here in California, but we really find this down at the bottom of the ocean floor. All right, so if you were to go down to the bottom of the Pacific Ocean or the Atlantic or the Indian or wherever and get away the sediment on the bottom, actually look at the bedrocks down there, it would be basalt. Okay? And we'll get into some of the importance of that, again, when we get into plate tectonics. But it's mafic, meaning it's rich in iron and magnesium. Okay? And so that's it. There's some things we'll cover later on about the importance of that. But right now, just know that's what's in it. And also, it makes it darker in color. Right? So the felsic stuff, much lighter. Basalt is typically a very dark gray to outright black that we're dealing with. Okay? But again, fine grained. You can see some, stuff in there, but it pretty much just looks like the same stuff throughout because it cools quickly and it doesn't have time for those different atoms to bond together to crystallize to form the different minerals. And just, I don't know if I mentioned it or not too, like the penny right here, when you see this kind of stuff, just everyday objects next to things, it's for scale, right? It's there so you know that we're dealing with a rock this size and it's not some giant boulder or some tiny little thing or whatever. So you'll see a lot of pictures, especially now as we're getting into more, stuff from the field. We'll see examples of you kind of use whatever you have just to give some scale there. You put sunglasses or even a ruler itself or whatever next to something. So when you take that picture and you go back and look at it, you have a sense of what it actually looks like, right? Or how big it was, or so you can compare it to other stuff. So that's just what that means. We have examples of really amazing igneous rocks. California is a great place for this stuff because we are so tectonically active. We've had, earthquakes galore, mountain building processes have happened quite a bit, volcanic stuff. We've just got a lot going on. And if you go up, not too far from here, but up near Mammoth, you can go to the Devil's Postpile National Monument. Don't do it now because we're staying at home, but, when it returns to normal, you can check this out if you haven't seen it before. But what this is, it's a big lava flow that cooled. So this is extrusive igneous stuff that we're looking at. And when it cooled, part of the lithification process is where we've got these hexagonal or six-sided columns that form. You can see a little pocket knife right there. There's another everyday thing for scale, but it's simply these things formed in these amazing six-sided shapes simply because of how this stuff cooled and the stuff inside there, right? And what's extra just Californian about this too is not only do we have this lava flow thing and the remnants of that, but these gouges in here, that's from glacial activity. All right, so we had this fire raging through, this incredible lava coming through, It cools. Years later, Ice Age, ice comes through, carves up this stuff. And we'll talk about glaciers later with this geomorphology stuff because it's important to California geography in general. But there's just a great example, not too far from here, just this amazing extrusive igneous stuff. I mean, the Sierra Nevada are incredible intrusive landscapes that we've got, but we've also got this extrusive stuff. Devil's Tower in Wyoming, same kind of deal. In here, where we've got those columns that we're seeing here, pretty remarkable. And this is what's left behind. We have this mountain of solidified lava, these extrusive rocks just kind of erupting out of the ground here. All right, so there's our igneous things. So remember, igneous rock, fire formed, anything that comes from cooling magma or lava. And then we have intrusive igneous rocks or extrusive igneous rocks. Again, whether it did cool from magma or whether it did cool from lava. All right, now sedimentary rocks, or we can think of these as recycled rocks. So where it's broken down particles of rocks and minerals and stuff like that. A lot of this starts out as igneous, maybe. Say the granite of the Sierra Nevada. It's exposed, up here we have these mountains here, but stuff is just beating against it. Weathering, erosion, all sorts of things. Whether it's glaciers coming through, or water coming through, or wind, or some of this stuff we'll cover when I get into geomorphology. It's just beating against the rocks, breaking them down into smaller bits of rock, and that rock can be carried away, transported elsewhere, piled up, and then eventually goes through a lithification process, so it becomes a new type of rock, a sedimentary rock. Okay, that's the general process for how this works. But again, so we are people of science, we're going to get into 3 distinct subtypes or subclasses of sedimentary rocks here. We've got clastic sedimentary rocks, chemically precipitated sedimentary rocks, and organic sedimentary rocks. Okay, now clastic, this first one, like clast really means a fragment of rock. Right? Again, I think this one might be Greek. I'm fuzzy with these ones. I can't remember. But it simply, when you see clast, it means broken bit of rock, fragment of rock, whatever. Okay, so a clastic sedimentary rock is simply a bunch of fragments of rock that break off of some other existing rock, get carried away to some other location. They have a layering process occur where it just gets piled up year after year. More stuff gets carried along. Like this sample right here is sandstone that we're looking at, and you can actually see the layers in here. These different colors, the different bands of color in there, those would be different layers of sand that have been carried down, and sand is simply little bits of other existing rock, right? So it gets carried away to some other place. Typically it's from the top of a hill, you go down to the bottom of the hill, and this stuff gets laid flat, horizontally, in this way. And then other stuff will get piled up on top of it. So the different colors can indicate, I don't know if you guys heard that sound, that just scared the hell out of me. I have a neighbor who has a Dodge Viper, which is, if you don't, it's a ridiculous car. And whenever he starts it, it gives everybody a heart attack because it's got that thing going on. So that's, you can probably hear it, I'm guessing. That's what just happened. All right, let's move forward. So yeah, the layering, the reason we have these different colors, it can just be different minerals or whatever that get broken off at any given time, right? It's a different chemical composition of the material. And that's why we can see these different layers in here. So this stuff is gets piled up, and then over enough time, you'll have this squeezing together. There's always water involved with this stuff, and it'll start these chemical reactions and this cementing process where these particles of sand, in the case of sandstone, actually get glued together. Okay? And really they lithify, right? Again, this lithification, it really does become a rock, right? It sounds like when you say other bits of rock getting glued together. It sounds kind of cheesy, but it really does become a new rock. And again, you'd be holding sandstone and some shale and some of this different stuff in the classroom. Can't do it now, but it is clearly lithified. It is turned into something new. It's no longer that igneous rock that a lot of this stuff started out as, because it's made up of a bunch of different igneous rocks and a bunch of different stuff, and it's transformed into a totally new thing, a recycled rock. Right? So that's what a clastic sedimentary rock is. And with sandstone, you can feel it. It feels like sandpaper, which is, sand glued to paper, right? You can feel the grains of sand. And really, clastic sedimentary rocks in general, they're simply little fragments that do get lithified. So up here, we have sandstone, right? So if you were to feel this, you would feel that rough sand. We have shale down here, it's simply clay. That's little, and clay is simply smaller bits of sand, but it's clay that gets lithified together. So that would feel smoother. Conglomerate is where we have gravel and big boulders and cobbles and stuff get lithified. All right, so we have the that you can see the big rocks inside here. It's all the same process, just the different grain sizes that we have in here. You can also see in this shale we have little fossils in there. I'll talk about fossils, for a little bit here, and we'll cover that. But we find fossils in sedimentary rocks, quite often these clastic sedimentary rocks, and those can be quite useful for the historical geology, of which we will speak next time. All right, so that's clastic. Okay, little fragments glued together, lithify into something new. Chemically precipitated sedimentary rocks it's the same process, and that it's this recycling, it's these fragments and stuff like that, but it's where the fragments themselves, the broken bits of rock or mineral or whatever, they actually get dissolved. Okay, meaning they disappear into water. Okay, and so it's the idea, like you go to the ocean, and actually don't go to the ocean, right? Stay at home. In fact, you can do this if you don't believe me. You can take, a glass of water. You can, just pure water there. Add some salt into it, right? And as you're adding that salt, you can see it's, they're crystals. It's, in that rock form that we've got. You can put that into the water, and then if you stir it around, the salt will dissolve, right? So that you can't see these things anymore. The crystals vanish, right? They're still there. They're in the water. They're just being transported in solution. Is the chemistry term for this stuff. So if you were to taste that water, you could taste it. Right? It's very obvious that there's salt in there. Don't drink too much of it, but it's invisible to us, right? So it vanishes. Now, if we were to leave that, and you can even do this, like what else are you going to do, right? Don't put it in a glass. Put it in a little bowl. And right now, it'll still work probably, even though it's raining outside when I'm recording this and all that. But you can wait for it to warm up. If you want, make it move a little faster. But if you have, say, like a bowl of water, put just enough water in there, add some salt, make the salt go away, but just leave it by the window, for the afternoon. The water itself will evaporate as it starts to heat up. And as that water evaporates, it converts to vapor. It disappears, right? It goes up into the atmosphere. We talked about that in the last section. But as that stuff disappears, the salt is left behind. Right? It's precipitated. Is the idea here. It's a precipitate. It's left behind there, and it will recrystallize. So at the end of that afternoon, your water's all gone, but you have this layer of salt down at the bottom of that bowl. Okay? And if that happens with enough time, these things, as the water continues to evaporate and these minerals are left behind and get stuck together, we get a chemically precipitated sedimentary rock. Okay, so it's the same idea. It gets piled up, layering, lithification happens. It's just we have that dissolving. That's part of it, right? So that's what makes a clastic sedimentary rock different from a chemically precipitated one. And this image we have here on the screen, that's limestone. Okay? And so limestone, pretty fantastic. It came from like seashells and stuff in an ocean, right? So, and it's not the actual like crab or whatever that's in there, it's the shell itself, like the calcium in there. It dissolves into the water. And when we have oceans, vanish, which happens over 4.6 billion years, we've had a lot of stuff happen in terms of the movement of continents and land masses. We've had climate change, we've had all sorts of stuff occurring. I'll get into this with tectonic activity, how some of this stuff works. But when you have an ocean vanish, which you can have like near the coastline, as continents start moving, stuff gets pushed up, the water kind of gets more and more shallow, and it's the same thing. Like if you have that bowl of salt water, on your counter near the window, same kind of idea. That ocean water goes away, the hard parts, the seashell stuff, is precipitated, left behind, piles up, lithifies, and limestone is the result. So meaning that wherever we, are looking around and we find limestone, which we have, up and down in California, that part used to be underwater, right? That used to be an ocean. That's what it's saying. We can see a lot of limestone and similar types of chemically precipitated rocks throughout the Central Valley, for example, because that was underwater in between when we had the Sierra Nevada, get built up, and then we had the coastal ranges get built up. That pushed the ocean, the Pacific Ocean, further away. These, the oceans, more interior disappeared. Limestone is left behind, right? So that's what limestone is. And another example, these evaporites. This is actually exactly what I was talking about. We're out in the desert. We'll have rainfall. We have a lot of what we call salts. So it's, salt itself, but it's also gypsum, some other stuff that's like salt-like in it. But it's all throughout desert soils. And this stuff in a non-desert area would be washed away, carried out by rivers, taken to the ocean itself. That's why we have, salty ocean water. In the desert, we don't have water stick around enough to carry this stuff away. So we've just got this very salty soil out there, right? But when we do have periods of rain, I'm doing, what is it, April 10th, when I'm recording this here, 2020, it's been raining nonstop, here in the Antelope Valley for 2 days now. The water just keeps coming down, but we don't have river networks and stuff to just quickly get it out to the ocean or have it carry along. So it's just kind of churning up a lot of those salts. They dissolve into the water. Eventually, this water is going to evaporate. As the rain clouds go away, temperatures go up, and so all that salt is left behind. All right, and so in Death Valley here, to great pictures, you can see the mountains reflected here. So all this is water, and then soon after that water is gone, it looks like snow, but these are salts in the area, just left in this spot, and they will pile up year after year, and they lithify, and they make this layer of this, rock salt that gets chemically precipitated and then lithified in this way. Right? We call these evaporites. Just kind of a general term for it. All right, so that's our second type, and then our third type are what we call organic sedimentary rocks. And I should warn you too, if you've taken a geology class or look this stuff up on YouTube or on the internet in general, some different geology textbooks, geologists classify this stuff in different ways, right? So you won't see clastic, chemically precipitated, and organic. You'll see some other variation of this. It's all it's the same stuff. Clastic is pretty standard. It's when we get into this term organic, when it gets kind of fuzzy, this is just the classification system we're using because this is the stuff I learned, and we're going to be consistent. All right, some geologists would hear me talking about this and go, "Oh, that's the argument." This is what we're doing. All right, so organic, really all we're talking about here is coal. Okay, coal used to be organic tissue. right? Animal plant tissue. And it's the idea this stuff formed starting millions of years ago. You can see with this image right here, we have this swampy area, a lot of plants, a lot of different organisms swimming through here, living here. When they die, whether it's, plant matter just falling into the swamp, or, fish or frogs or whatever it might be, just, dying in here, all of this organic matter falls into the swamp and will slowly, start to decay, gets piled up. Over time, we have heat, pressure, water moving through here. Again, this lithification process takes place, and the result today, again, this starts millions of years ago, but today we find coal, which is this lithified remnant of this past environment, of the organic material that was here, right? And so coal is therefore flammable. We can burn it, and we get a lot of energy from it, and that's why we know of it and use it and all of that. But the reason why this rock can, be set on fire is because it's made up of organic material. Okay, so that's our definition, and really, coal is just that one lithified form of fossil fuels in general, a term we use to describe this stuff. We call it fossil fuels because it started, as I said, millions of years ago. It's dinosaur stuff, right? That is decaying, and so it took millions of years for it to either lithify or become, the liquid form, like petroleum, or what we just generally call oil right here, or the vapor form, which is natural gas. It's this byproduct of these decaying, prehistoric things, right? And this is actually, this, just because it's kind of interesting, this is how we know where to look for some of this stuff. So again, a physical geologist would, could specialize in these fossil fuels and being able to go out, map the landscape, read the landscape, get a sense of where you could drill for oil and have a really good chance of finding it, versus places where you might as well not even bother, right? And it has to do with these folds in here. This is all connected to plate tectonics. We'll get into how rocks do this. But in these folds in the landscape, this is where oil can get trapped. So as you, drive around Southern California, we've got oil. If you drive, again, down the 14, head, down into Santa Clarita and eventually down into LA, you'll look around in the hills, you can see, these jack pumps working and all this evidence of oil. It's because of the folding. It's because the actual San Gabriel Mountains themselves have trapped oil, and we figured that out. We're able to, pull it out. And of course, all this stuff is terrible because it's destroying the climate, but the reason why it's been so useful is because just from a pure energy standpoint, we get a lot of energy out of this stuff. It's why it's been so useful, whether, starting as coal or, using, gas for our cars and, natural gas, as well as a way to heat things, as well as to, move vehicles and stuff like that. It's very easy to use for a power source. We get a lot out of it. The problem is it's adding all sorts of CO2 to the atmosphere. It's destroying the climate. So it's, terrible. We need to get away from it, right? But this is what, a lot of geologists have spent their time doing, is trying to figure out where this stuff is, because before we were aware of all this climate change stuff, it was just this great, wonderful energy source, and we wanted to find more and more. Okay, but coal itself, it's that organic sedimentary rock. All right, so as I said earlier, we find fossils in sedimentary rocks for the most part, and it's because, like igneous rocks, we're not going to find fossils in there because the stuff is molten, right? Any organic, creature, plant, whatever, if it's in lava, it's going to, completely melt, and we're not going to have any record of that. So we typically find this stuff in sedimentary rocks, and with them, it's worth mentioning that fossils themselves, like this Tyrannosaurus rex, I assume that's what it is. I just Googled something. This dinosaur, thunder lizard that we got right here, the bones that we're seeing aren't the actual bones themselves. Okay? It's not organic. And that's what, Jurassic Park. So we had to have the mosquito or whatever it was to get the DNA. There's no DNA in these fossils because the fossils themselves aren't actually organic material. What happens is, as sedimentary rocks, are being formed, like let's just say clastic stuff. We'll use, shale as that great example where you have particles of clay that are getting piled up in an area over time, right? You've got the layering, we have that lithification. We'll have something die, like the, Tyrannosaurus or whatever it might be, and it falls into this clay and it also gets buried, pretty quickly so that it's not, a bunch of scavengers coming around and pulling stuff apart and moving it around and all that. Like if we find a pretty good, almost complete skeleton or whatever, it means it's been buried quickly. All right? And so more clay gets piled up over it, and so nothing's messing with it. And then as it's decaying slowly, we actually have minerals coming in and replacing the organic material. And it's doing so in the exact shape of that organic material. So these are what the bones would have looked like, but it's not actual bone in there. It's a rock. That's what a fossil is. It's a rock that happens to be in the exact shape of that once living organism, right? So and these are, as we'll see, they're great for understanding what the earth, was once like, right? Because we get a sense of what these past animals and plants and stuff, were like, what they look like. So they can tell us quite a bit. And in part, it could just simply be the the animals themselves. We get a sense, okay, we're finding a lot of sea creatures in this area, even though it's on, it's land right now. If we're finding, fish and shells and stuff like that as fossils, we know this used to be underwater, right? Whereas if we see stuff like this, we know, yeah, it had to be, above water. It was land. It was this terrestrial environment because you have these land creatures, walking back and forth and operating here, right? So just the types of fossils tell us something. In fact, this pop quiz, what kind of dinosaur fossils do we find throughout California? I'll wait. He's shouting. I hope you're all shouting at your computers or phones or whatever at home. Trick question. We got none. I mean, they try to say there's like one Allosaurus leg or something that was found, but that seemed to go down a river and was brought in here. We really don't have dinosaurs in California at all. And why is that? I already hinted at it earlier. That's right, class. It's because we're new, right? The state didn't exist, at the peak of the age of the dinosaurs. And technically, dinosaur means these things that were on land. So we'll find a lot of sharks and stuff like that. Like we have those in like near Bakersfield. Some of you guys, I don't know, may have gone. Like one of my kids went there on a field trip where you can go to this. It's like Shark Tooth Hill or something like that. And they got a bunch of shark fossils and stuff in the hill, and they let kids dig this stuff out and take it home. And you don't find a Triceratops horn or anything like that. It was all this water-based stuff, right? Because we didn't exist when we had these T-Rexes and Stegosauruses and all this stuff walking around. We'll later find fossils of mammals. That's the cool La Brea tar pit stuff, the saber-toothed cats and the mammoths and stuff like that, because we did exist when the dinosaurs are gone and we have this age of mammals, right? So that's one way we know what we know about the geologic history of California. And we can also, it doesn't even have to be, just that we don't have to find the organisms themselves. You can see some stuff like red sandstone lets you know that this stuff formed. That's oxidation. It rusted and all that. So this stuff formed on land, whereas very black and dark shales typically means this stuff formed deep in the water. There's no oxygen there, right? So just the color of this stuff can tell us a lot. So fossils are great. We'll talk about that. We also see another cool thing about sedimentary rocks. It's the layering, right? Or what we call strata. All right, stratification refers to these distinct layers. And so one layer is stratum, and then multiple is strata. That's how you use these words here. But these can tell us a lot. And we'll play around with them. I'll show you how to read this stuff briefly, give a very brief introduction to reading rock strata, because that can tell us a lot, again, from this historical standpoint, in terms of like, what came first, how did things change over the years, and so on. So just these layers, not only do they look cool, but they can tell us a lot. And the Grand Canyon and all the canyons around the Colorado Plateau and throughout the Southwest, they're great examples of strata, and a lot of it exposed. So the Grand Canyon, roughly 5 million years ago, the Colorado River just started cutting down rapidly through here, exposed all of this stuff, and you can see the different colors in here. And we have different types of rock. There are igneous rocks and sedimentary rocks and stuff in there. But just being able to read the strata, it tells a story of what happened. And it's how we know what we know about this part of the world and the Colorado Plateau and how the Grand Canyon formed and so on. So reading the rocks, that can give us a lot of information. And we'll see some of that next time. All right, let's move on. Our last classification here, we have our metamorphic rocks. Okay? And so a metamorphic rock is one that has transformed. It used to be igneous, or it used to be sedimentary, but it transformed, and not through this recycling, but through an actual recrystallization. Okay? Where the atoms in there freak out and they recrystallize. They come back together for something new. Okay? So it's a sedimentary or igneous rock, but it undergoes a lot of heat and a lot of pressure. Okay? So it's not enough heat for this rock to melt, because then it would be an igneous rock, right? So it gets really hot, but it doesn't reach that point where it starts to melt. And the pressure is where it's, this material is getting squeezed together. And so for both of these things, we find metamorphic rocks deep in the, or I shouldn't say we find them everywhere, but they form deep inside the earth. All right, so it's an igneous rock or a sedimentary rock that was maybe up here at the surface, but through these tectonic processes, again, stuff we'll get to, it gets shoved deep inside the earth. There's a lot of heat down there, and that's because of this radioactive decay. I think I'll be talking about that a little more next time in the historical stuff, but it's just these radioactive isotopes that are falling apart, right? That's what this decay is. And as this happens, it releases heat, and that's why we have, liquid rock, deep in the surface, magma, as well as like our liquid outer core and all that. It's just liquid metal at the center of the earth there. It's because of this radioactive decay. All right, so that's from where all the heat inside the earth is coming. And so that is where we get enough heat to where this stuff can start to transform. And then the pressure is also from tectonic stuff, where you can have literally, two continents being shoved together very slowly, right? It's not like a car crash or something like that. It's a slow process taking, millions of years for real significant stuff to transform. But through this process, we get that heat, we get that pressure, we can get a metamorphic rock. And it effectively, like I said, the rock, it freaks out. What it once was, the minerals inside there recrystallize, we get something new. This image here is an example of a gneiss, and it's spelled, Gneiss. This used to be granite. I think this specific type, there's some different types of gneiss that we have. So it started out as an igneous rock, underwent this heat and pressure, transformed, and you can see the zigzag kind of accordion lines in here. That's the pressure, right? That's it being squeezed together. And so what this is showing, these are actual different minerals in here, but they maintain this alignment. So the lines in here, that's a specific pattern. It shows us something about, the pressure itself, which is cool. But when we see these minerals aligned in this way, we refer to it as foliation. Okay, so foliation means it's not layering like with a sedimentary rock. It's not stuff getting piled up on stuff, even if it might kind of look like that. It instead is where we have some kind of alignment with the minerals themselves. And this alignment happened with that recrystallization. So it's the result of this metamorphic process, right? So an example of foliation would be, going back to this, the zigzag lines here. Okay, so there's foliation in this rock. Slate, which was once shale, so it was clay, right, that lithified. It's that clastic sedimentary rock. When it undergoes this metamorphic process, it becomes slate. And we don't see lines in here necessarily, but it flakes off in these sheets. So like you can just see it, like the cracks in here. That's another example of foliation. And slate, it's something we use for a variety of things. Like pool tables traditionally are made with slate because it's very hard, durable stuff. It can withstand, as you're knocking pool balls all over it, it can, maintain its integrity there, right? You won't have little dips and divots and stuff like that. So it's very tough, but it's also easy to work with for stuff like that because it breaks off in these sheets. And it's also, we use it for tiles and things like that, flooring or whatever, because it just works. You can work with it easily, even though it's a very tough material. But that foliation, it's because of the way in which the minerals align, it breaks off in these sheets. So it would have foliation, right? Whereas quartzite was once sandstone. So again, another clastic sedimentary rock. It's little bits of sand glued together. Our result is quartzite. We don't see foliation because there's no actual alignment, right? We see a bunch of different stuff going on in here, but there's not some clear, organized pattern at work, okay? So we don't really have sub-classifications of metamorphic rocks. We instead say we've got metamorphic rocks that have foliation or do not have foliation. All right? Hopefully that makes sense. And this, you don't need to know any of this stuff or memorize it, but it's just kind of cool to see like exactly how this stuff works. And we have very consistent transformations. Like we already talked about sandstone and quartzite. It's going to be at a certain temperature, roughly 800 degrees Fahrenheit, a little over, 400 degrees Celsius here. It's when sandstone gets to that temperature, that's when it actually transforms into quartzite, right? Or here's shale and slate. Lower temperature necessary for that to happen. Okay, but it is a consistent thing. When shale gets heated up to the right temperature, undergoes the right pressure, all the conditions are right, it's always going to turn into slate. It's not like some mystery grab bag that it might be, marble this time and quartzite that time and then slate or whatever. No, what it is it's always going to be shale turns into slate. We always have limestone. Remember the little sea creature stuff? That always turns into marble, right? So that's, something to think about. Another thing we use for like, countertops or tile or whatever, it's been used to carve sculptures and stuff like that. That actually used to be little sea creatures hanging out in an ocean. Bits of their seashells dissolve. Ocean goes away. This stuff is chemically precipitated, turns into limestone. More time passes, more changes, take place. There's enough heat, there's enough pressure, it transforms into marble. So it's pretty remarkable to think about what has taken place here, right? How much time has gone on, how much traveling these rocks have undergone. And that's this whole idea of the rock cycle, is that this stuff is constantly changing, geologically speaking. Like it takes millions and millions of years, but it's still, nothing is still or finished or in some end state on the planet. Right? Sandstone, quartzite, same kind of deal. That clastic rock is going to transform into this metamorphic rock that is quartzite with the heat, with pressure. All right, is this making sense? You guys a little physical geologists? You feeling confident? Feeling like you got this stuff? All right, let's see. Pop quiz. What are we looking at here? Huh? What is that? I'll wait. Let's see. And this is fun in class because I'd be saying like, what is it? And like two of you would shout some stuff out and it'd be horribly wrong. And I'd say, wrong. You're horribly wrong. And then you'd kind of like get quiet, not want to talk, and then I coax you. Like, it would be delightful. We don't have that. So I guess just pause this while you look at it, but try to think about it. And what this is, hopefully you could figure this out. And the clues, just so you have little bits of rock that are glued together. This is smoothed out because of, being in a river. So it's the water abrading this and smoothing it out. Some geomorphology stuff we'll talk about later. But if you look at it, this isn't the same as what we've seen where it's like with these igneous rocks. These are actual fragments of rock that are glued together. So if that is the case, it's got to be what? Clastic sedimentary, right? And this is specifically conglomerate because it's bigger hunks of rock. It's not sand, it's not clay, it's not silt or whatever. It's this gravel that's been glued together. So if you said, this is the clastic sedimentary rock conglomerate, perfect. A plus, right off the bat. But don't get cocky. So what's this? Yeah. I guess pause it, think about it, and you probably shouted granite. If you saw that, and you're horribly wrong. It's not granite. It's actually diorite, which is like granite. I picked this just to be a jerk. So diorite is an intrusive igneous rock. And we know this is an intrusive igneous rock because it doesn't have that look of little fragments glued together, right? These are large grains of minerals that have started to form as this thing was slowly cooling, right? So the large grain size, this is diorite that we are looking at right here. An intrusive igneous rock, it's similar to granite, same concept of how it forms, just some different stuff inside it, right? So intrusive igneous, if you can get that, fantastic. That's where you should be. What's this? And you probably, because students typically shout, it's fossil. I don't care about that. What type of rock is this fossil in, or these fossils in? All right? It's got to be, based on what I said earlier, sedimentary, right? Because that's where we find our fossils. And specifically, I mentioned this earlier, it's shale that we're looking at, which is clay, which is very fine-grained stuff. And it's kind of hard to see if you can't feel it, but this wouldn't feel like sand. It would feel very smooth because it's the much smaller grained clay that's lithified, that's glued together. So that's what that one would be. So it's shale specifically, but at least you can hopefully find it's a clastic sedimentary rock. Ooh, what's that? Come on, what are we looking at? See those lines in there? What are those lines? What do we call that? It's not layering, it's not strata. It's foliation, because it's the actual, this isn't the result of stuff layering over time. It's the minerals themselves have aligned in a specific way. So we call that foliation. And we only use that term for what type of rock? Rhymes with metamorphic. Perfect. Metamorphic. Very good. And this is another example of gneiss, right? Like we saw earlier, the wavy lines in there, that's that cool compression at work. So that's metamorphic, and we know it because of the foliation lines and because just the pressure itself. And we'll get into talking about layering later, stratification and all that with the historical stuff, but we don't see sandstone, like layers of sandstone. It doesn't form in this kind of wavy manner here. It would look much different, right? So just looking at that, it's got to be foliation. All right, so there's that. What's this? Ooh, have we seen this? Have we discussed it? We kind of have, but this is the bonus round here, the quiz. You get it? Oh, okay, yeah. Pause it. Think about it. What are we looking at? What are our clues? We've got, all right, hopefully you unpaused it now because you've locked in your guess, and hopefully you said basalt, which is an extrusive igneous rock. And if you did, my God, you are so good at this. And if you didn't, shame on you. I want you to go back, listen to this lecture 3 more times until you get it. At least 3. Do 4. You're not doing anything else. You're staying at home. No, this is very different from the basalt that we saw. So this one's trickier here. The clue that we're dealing with something that is an extrusive igneous rock, It's the holes in there. We would call this vesicular if we're being obnoxious geologists. Instead of saying it's full of holes, we say vesicular to describe these holes that are the result of gases that were in the lava that escape, right, that are being released into the atmosphere up here on the surface. But because this is cooling so quickly, right, the gas escapes, but it's also lithifying at the same time. So these little pockets in here are left, we have the holes that are left. If it were an intrusive igneous rock, you're still going to have gases. These things are going to escape, but because it's cooling so slowly, the holes would collapse in there and you wouldn't see it, right? So we have these vesicular rocks. It has to be extrusive igneous. So it's as lava's flowing out, gas escapes, but it lithifies quickly enough to where it's like this. It has this holy appearance to it. It's also dark in color, relatively speaking, and this one's kind of grayish, but it's got to be that mafic rock as well. That's one of the clues that it's basalt. It's also kind of hard to say because you can't feel it. Because you might have said pumice, or scoria is another one that I could see. Nobody said scoria, but you could say that. Like with pumice, it's where we have the holes in there, but it's enough to where pumice can actually float. There's so many holes. It's less dense than water. It can float on the water. It's effectively the same idea. It's another extrusive igneous rock. This specific sample, not that light. It is basalt, but that's the clue. These holes in here, right? So if you at least, knew there was something going on with the holes there, we're thinking volcanoes, we're thinking extrusive igneous. Fantastic. Excellent work. And like I said, if you didn't get any of these right, or even missed one, go back and listen to this. Do more. My God, sick of me. Or don't. I'm not going to test you on this stuff. I'm not going to show, pictures of these rocks. I just want you to have a sense of what makes an igneous rock different from a sedimentary rock and from a metamorphic, and also know what's the difference between these different types of igneous or sedimentary or metamorphic. All right, so go through that. Think about this stuff. Fantastic. And like I said, I'll tell you exactly what you need to take from this for the test. Your third test that we wind up having, but there's going to be something about these different classifications of rocks. So go through there, make sure you get it. And next time, we'll get into historical geology, which I think is way cooler because it's not listing off these categories of stuff, but it's telling the story of what the Earth has done as well as how we've figured it out. So I'll get into that next time, but for now, just have fun with this rock stuff. Try to stay safe and sane, and I'll be talking to you guys later.